Hello and welcome to the second webinar considering acoustics and the natural and hybrid ventilation of buildings. My name is Benjamin Jones and I'm an assistant professor here at the University of Nottingham's Department of Architecture and Built Environment. This webinar today is being run by the CIBSE Natural Ventilation Group, and so if you're interested in the group and its outputs, then you can find its webpage on the CIBSE website, www.cibse.org, under the Networks tab and the Groups section. Naturally ventilated buildings use openings located in their facades to simultaneously supply fresh air and extract stale air. However, these openings also allow the ingress of environmental sounds, which, when they're unwanted, unpleasant, loud, or disruptive, are defined as noise. The very size of natural ventilation openings means that noise ingress can be significant, and an unintended consequence may be that occupants seek to control it by closing ventilation openings, which in turn can lead to underventilation, poor air quality, and overheating. However, there are solutions achieved by carefully balancing all competing factors by using good models, through intelligent product selection, and by the application of clear and intuitive guidance. Our previous webinar considered acoustic and ventilation issues in residential buildings and can be found on CIBSE's YouTube page if you want to listen again. However, non-domestic buildings are generally bigger and more complicated than houses and pose a completely different set of problems. They have a greater number of systems and services which themselves might be the source of noise, and they have a greater geometrical variability that affects the transmission of environmental noise into a building. Here, it is really important to assess the potential for noise transmission using surveys on existing buildings or by modelling future buildings. Then, appropriate sound insulation can be identified and installed. To support engineers and their ventilation designs, there's a lot of good guidance available, but it isn't always properly understood or used appropriately. Acoustic problems are a significant source of commercial risk, and so a working knowledge of appropriate guidance, assessment techniques, and modelling methods is required to solve engineering problems. These topics provide the context for our discussion today. You can follow slides as we go, and at the end, you'll be invited to ask questions, and you can do this using the questions section of the GoToMeeting dashboard. I would prefer it if you ask questions rather than make points. It just makes filtering them easier for me. Our two speakers today are Zay Nunez and Owen Connick. Zay is the director and founder of Mech Acoustics. He believes in lifelong education, so when he's not on site reviewing designs or grinding out the paperwork, he lectures at the University of Bath. He also delivers CPD events and is known for writing papers too. Zay relishes the interdisciplinary challenges of great architecture and is always ready to break with convention in the quest for better answers. Owen Connick has had a promotion since we wrote the scoping document for this webinar and is now the technical director at Breathing Buildings, where he heads up the design and consultancy teams. Owen has a PhD in fluid mechanics of hybrid natural ventilation from Imperial College London and wide experience in the use of simple analytical models and water bath modelling. Since joining Breathing Buildings, Owen has developed significant expertise in the application of dynamic thermal modelling. And he uses these to simulate environmental quality in real buildings with a focus on schools and UK design regulations. The question that Zay and Owen have posed to us today is, why are acoustics important for natural ventilation? And you'll hear Owen speak first.
Thanks very much, Ben. Yes, I'm sat here in Bristol with Zay, and we are going to try and address this question of why are acoustics important for natural ventilation. I'd like to thank everybody for joining us this afternoon. The way we're going to work through it is with three sort of key questions that we're going to pose to you guys as the listeners. And as Ben said, please do throw questions back at us. Starting off with why acoustics are important with in terms of natural ventilation, and then leading straight into what the different factors are which pull on ventilation design. Once we've kind of had a brief run through the different factors that pull on ventilation design, we'll look at what tools are available to aid designers in balancing the competing tensions on ventilation design, and with a strong focus on the competing tensions around ventilation and acoustics. So those are the three sort of key questions we're going to try and address today. Starting off with why it matters then, and thinking about some of the health implications of noise levels. Elevated noise levels, and that doesn't need to be significantly elevated, but particularly if there's long-term exposure, can lead to annoyance, irritation, frustration. Particularly speech intelligibility and hearing impairment are well-known results of extensive exposure to elevated noise levels. But then further than that, hypertension, sleep disruption, and many other actual medical illnesses are linked to elevated levels of exposure to noise. In the UK, there are numerous standards and requirements, regulations governing these. So the particular standards for non-domestic buildings is the British standard BS 8233. And in particular, the Building Bulletin 93 covers acoustic standards and guidelines for acoustic design in schools and education buildings. I find this quite interesting because in the natural ventilation world and in the hybrid ventilation world, we find the school as an education sector is actually quite forward-thinking in many ways. And it's interesting that in terms of the acoustic, schools have their own dedicated design guide as well, which is to the credit of the Education Funding Agency for putting out those kind of publications. So hopefully in a very brief way, that justifies why it's important. One of the things Zay and I have discussed previously in terms of regulations is they tend to be quite dry and boring, but ultimately, because there are regulations around these standards, one always has to design a compliant building. That is not an option. What the option we should be looking at is how far we can push the boundaries of design to improve upon the minimum design standards. And that's kind of what we'd like to talk about a little bit today. So, okay, so ventilation design, as this kind of cartoony graphic shows, is pulled on or is intentioned by a number of different factors. So obviously we ventilate buildings to provide thermal comfort and to guarantee good air quality. But by ventilating the buildings, that should not be at the expense of poor noise quality or high energy consumption, or indeed a fifth factor, which isn't on here, which is high capex cost. So with these different tensions pulling on the ventilation design, it's important to keep them in balance, not to focus primarily on any one factor, but to try and manage them so that you get an overall holistic design which incorporates the benefits of each. And actually, the design stage can enable significant savings in all of these things, significant savings on exposure to noise, significant savings on energy consumption, and significant benefits in terms of thermal comfort and air quality by looking at it in a rounded, joined up way. So what we'd like to do is pull upon a few different tools, and we've kind of bucketed them into three headings here: site mapping, ventilation design for building layout and ventilation type, and then ventilation design for facade and vent shaping. And the three are not discrete, but we want to break them up. We want to dive into a bit more of the detail of each in turn, and then at the end, we can pull them together, and hopefully it'll lead to some interesting conclusions and some interesting queries from the guys who are listening in. So if we start off with site mapping, then I'll hand you over to Zay, and he can talk you through that.
So just...
Actually, I'll just whiz through these. So just to introduce the topics of site mapping, essentially what you've got is a Google Maps photo on the left of a site, which is a school in South Wales. And what we would do in site mapping is we extract the geography of the site and we extract the geometry of the buildings and input those into a computer algorithm, which, as you can see in the bottom right, maps in a kind of color map style the acoustic levels on different facades of the site. When I'm talking about ventilation design, I'm going to pick up on these two key concepts. One is the massing of the building. So that's if you need to achieve a certain amount of floor space, how best can you position and assemble that floor space to manage both the acoustic requirements and the ventilation requirements. And then the second one in ventilation design is looking at different types of ventilation. So given a particular site, given a particular building, how can we ventilate that building in order to manage the restrictions that we have to live with? And then Zay's going to pick up finally later on in the presentation on this idea of facade vent and shaping. The idea of a window is not just a simple single item. It can be designed sensibly. And also the image you see on the bottom right shows different forms around the window, which are acoustic tools, if you like, or tools designed to manage the acoustics of the site. So those are the three concepts we're going to pick up in turn. And as I said, Zay's going to start off with the site mapping.
Thank you very much, Ryan. The site mapping that we're going to present is going to be split across three separate case studies. The three case studies represent different things. There's early noise mapping, detailed noise mapping, and then using noise mapping, possibly in combination with ray tracing and other tools, to really drive the acoustic design much, much harder. This is the school first case study. It's a primary school in the centre of Bristol. You can see the M32 kicking in here. This is obviously going to be incredibly noisy. So the advantage of noise mapping is it's going to tell us which layout is possibly the best layout for the selected school. So the first thing that we do is we import the site data. In this case, it's a relatively flat site, and therefore we don't include the topographical data. We've just drawn it on top of Google Maps. What we see here is the buildings that we've erected. This is relatively straightforward. It's just click and drag up to represent the buildings that are around the school. And then we can move on to the next three options. So this is option 1, this is option 2, and this is option 3. So if we look back at these, we have option 1 has got external circulation. If the sound reduction of an open window is taken at 15 decibels and the internal noise level is 15, sound reduction of an open window is 15 decibels and the internal noise level is 35, we shouldn't exceed 50 decibels for natural ventilation for openable windows. So this option here has an advantage that you can see all of this elevation along here can possibly be naturally ventilated just through openable windows, even down here in the corner. Option 2, on the other hand, has got the facade noise level, which is quite a long facade, at 50 decibels, so we can use openable windows here. But this elevation has got noise levels at 60. 60 is possible to naturally ventilate, but you're probably looking at an attenuated facade, which is going to have a serious impact upon the appearance of the building. The architect in this particular instance was quite keen on a 2-story option, bringing it closer to the road to maximize the use of the sites for sports and so on. But you can see here that the elevations are now at 65 decibels, whilst on the far side they drop down to 50. We've got to be a little bit careful that this is at low level. We can then map the high level floors to establish what the noise levels are there. The concept being here is that this data took more or less half a day's work to produce, and you can do this work at the very beginning of a project to maximize the benefits of the site layout. The next case study I want to present to you is more than comprehensive. This is much more about the benefits of detailed noise maps. We have the M32 traveling to the south of the site. It's clearly a very noisy site. What happens is we come across the bridge, drive around the car park the car, put the microphone up that we represent by this blue dot. Excuse me. This blue dot. And from here we can see the noise levels. And it's clearly going to be very noisy. But being on site, I noticed that the noise was predominantly coming from the west of the site. And if we look at the section through here and a section through here, we can see that there is a very shallow embankment on this side, whilst if we go further down to the east, there is a huge embankment plus a row of houses, existing houses that aren't going to get demolished before the school's built. The results, apologies. The result is a noise map that you can see the sound clearly coming from the west of the site across the school. This particular project, a previous acoustic consultant had worked on the job and specified that heat recovery units were required within the classrooms. And therefore, due to the excessive noise levels, it was basically a fully Mech vented building. What we then did was we calibrated a noise map of the existing school, which you can see here. The white squares are the measured levels, and the greens are the modeled levels, and the green squares are the measured levels. So in more or less every instance, bar this instance down here, the calculated levels are higher than the actual measured levels. And therefore, when we interject the new school, we can see that all of this elevation running down here, because it's facing away from the noise source, which is angled to the site as a result of the topography of the site, means that we can naturally ventilate all of these areas in green. This was a 3-story building, and there was a significant cost saving to be had as a result of providing a greener, more low carbon option. My third case study is Broxton School. This is quite an interesting school in that external noise levels are at 58 decibels, which is too loud for natural ventilation via openable windows. But what we do notice is that there's a very directional element of the sound to the buildings. So what we're using is noise mapping and ray tracing to establish what is the directivity of the sound, and can we combine that with the directivity of open windows. This is the data provided in various guidelines. So this is BB93 Acoustics for Schools, BS8233, the WHO, and so forth. And you'll see that there's about 10 to 15 dBs of sound reduction for an open window. What that means is that if noise levels are less than 50, as discussed, we can use openable windows, which is this area here in green. On the opposite side, at 54 decibels, they're slightly quieter because we're slightly further back from the measurement location. We would have to find a method of attenuating the facade. However, if we look at Napier University's work, where they carried out 425 separate sound tests, we actually see that their data stipulates that an open window provides between 15 and 24 dBs of sound reduction. So what we want to try and do is try and maximize the sound reduction up to 24, and therefore use simple openable windows rather than acoustic air vents. If we look at some of the results, we can see on this side in particular that the sound reduction of the window is much better when the sound is coming from this side of the window than if it's coming from this side of the window and traveling straight in. And this is what we would expect. As we open the window, the sound reduction increases greatly if the sound is on this side as opposed to on this side. Sorry, there we go. Apologies for that. So what we have here is the results of some FEA modelling. Here's the sound source, and here is a top hung outward opening window, and here is a top hung inward opening window with the sounds at the bottom, in the middle, and at the top. And you can clearly see that there's a significant difference depending upon which way the sound is coming to the window. So what we then need to do is establish what is the directionality of the sound outside of the building. So the first thing that we've done is to model it, as I've said. We then look at adding what we call the directional finder, which is an element here. So we put a series of arrays to pick up the sound. We then build a set of models with lots of different sound sources traveling down the sound source to provide the directionality of the sound. And finally, that builds us a pattern of the actual direction of the sound to the building. This is pretty much omnidirectional, as you can see here, and that's because it's a line source at a reasonable distance. If the building was to an angle, we would see possibly more sound coming from this side, and the closer you are to the noise source, the greater the level of directivity from the noise source itself. The final section is then to establish what is the effects of the building, and here we've used ray tracing, and you can see here the wave is traveling in, which is relatively straight because of the uniformity of the sound that we've already calculated. And then you can see here that there's a reflection. Although this reflection is considerably quieter, it will still have an impact upon the direction of sound along this facade here. Sorry. So this is the results. You can see here that this is the main sound coming from the west of the site, and this is the reflected sound. Combining the two together, we've more or less established that we can naturally ventilate the entire school simply by facing the windows in this direction away from the noise source, which is a really simple, clever, and cost-effective trick. So I'll now hand you back over to Owen to talk about ventilation design.
Thanks, sir. Yeah, I think that's a really interesting way to start out addressing the problem, is to look at the restrictions of the site, is to look at what can be done about understanding the location of the site and the location of the noise sources which it has to deal with. Once we've taken that into account, what I'm going to do is perhaps step forward and say, well, an analysis done has been taken on, and the site has been fixed. So here's a typical example of a site in Dudley, actually. And again, as some of the previous examples, it's a busy main road, and there's a proposal for 2 new buildings being constructed on the site. The top left image there shows the sound map, similar to the one that Zoe was showing earlier. And the color maps, again, show the intensity of the noise on different parts of the building. On the bottom right image, what you get is, on each facade, what is the typical noise level? And you can see that on the facades which face the road, you're typically at much higher than 65 dBA, which is very loud. On the facades which don't face the road, though, there is a significant noise reduction. And actually, it's got less than 60 dBA there, but that's a feature of the buckets that were chosen. The noise level on those facades was actually substantially lower. So what we looked at in this project was, well, are there other options for actually the shape of the buildings, other than these 2 linear plan versions, which can allow us to make better use of that quieter facade? So in the top left, you've got those 2 linear plan options, and in the bottom right, you've got what was called the donut plan, because instead of massing the rooms around a central corridor, the rooms have been massed around a central atrium. What that allows you to do is ventilate directly through the center of the building, and use the atrium to drive the ventilation flow. Now, that might not negate the need for ventilation openings on the facade, but it does reduce the free area required for ventilation on the facade, because you've got the atrium and a higher pressure difference driving the natural ventilation flow through the building. So whereas in the linear plan, any rooms on the facade which faces the road will, in all likelihood, need to be mechanically ventilated, in the donut plan, there is a potential to ventilate those rooms which face the noisy facade via the central atrium. And on the quieter facade, there's the facility to have smaller openings, which may actually be achievable. So I think that's quite a good demonstration of the link between taking the noise mapping, doing what you can to understand the site, and then using that information to infer what you do about the form of the building, and driving the form of the building by the ventilation design that you want to achieve. So let's take another step further now, and let's say that our building has been, it's set. So we know the form, we know the layout, and we take a typical room and we take a typical external noise source. So if I go back to the previous design, we might have an external noise on one particular facade of 55 dB. So what I'm going to do is run through a couple of different ventilation scenarios, which all provide, or all try and provide, a compliant solution based on that external noise source. So if we went with a naturally ventilated option, a simple naturally ventilated option, I should add, with, let's say, a sash window, and as I alluded to, most of the literature, most of the advice around says that the sound reduction through an open window is in the 10 to 15 decibel range, and this number of 13 dB is the widely adopted one in the industry. Questionable to those people who understand it a bit better, but the widely adopted number. So if we take a 55 dB facade and a 13 dB reduction through the window, we end up with an indoor ambient noise level of 42 decibels, which generally, in most places, and particularly in school design, would not be compliant with the acoustic regs. However, setting aside the acoustics and coming back to this holistic design approach, actually opening windows, indoor air quality is great, thermal comfort, good, energy consumption is, well, very low, 0 in this case in terms of ventilation, and the capex of an open window is quite low. So actually, yeah, acoustics is poor and non-compliant, but this concept enables lots of other benefits in the holistic design. So what are the alternatives? Well, sticking with the same external noise source of 55 dB, what if we assumed that we had to seal the window and mechanically ventilate the space? Well, that's not free. The mechanical ventilation comes with a certain noise contribution, and typically the mechanical vent system would then be designed to achieve an indoor ambient noise level less than 35 dB. That would be compliant. Indoor air quality and thermal comfort in a mechanically ventilated room would also be adequate, but the cost is energy consumption and the cost is capex, both of which are likely to be high. So You can win in some cases, but you can't win in all. Another option, what if we tried to use natural ventilation, but not directly through opening windows, rather through a roof terminal? In the top right of the image here, I've got a roof cowl showing ventilation inflow. One of the benefits of using a roof cowl is that if the noise level on the facade is 55 dB or that high, typically, or one might expect, that the noise level on the roof may be lower. It depends on the particular form of the facade. It depends on whether there's a parapet and where the noise source is, or where the type of noise source is as well. But in this case, we're looking at where the noise was traffic related, so it was at ground level. The roof level is actually considerably lower. So the noise pressure at roof level is only 40 decibels. And if we have a roof terminal, as I discussed with the donut plan option, you're enabling a more efficient cross ventilation and stack ventilation flow, which is more effective than a single-sided windows-only natural ventilation. So that means that if you do require openings on the facade, they are smaller in area, and we might be able to use an attenuated opening. Sound reduction through attenuated openings can be whatever you design it to be, but easily greater than 25 dB. So what this enables is natural ventilation. The indoor ambient noise level stays below 35 dB. We get all the benefits of Nat Vent in terms of good air quality, good thermal comfort, and low energy consumption. And also the CapEx is substantially lower typically than it would be for a mechanically ventilated or a fully sealed Mech vented building. The follow-on from this is that if we've designed a room which has such a natural ventilation solution, then when it gets very warm, we know that the natural ventilation is limited in terms of how much air we can bring through. Well, in the warmer days, we may, and this is a point of discussion, we may want to open the window further, accept a poorer level of indoor ambient noise level for a short period of time in order to manage the thermal comfort in the space. And in the same way as thermal comfort has adaptive comfort levels, one could argue that acoustics should follow a similar route and have adaptations. I'm very conscious of the fact that that could be quite a controversial statement, and I'm happy to discuss it later. But we still get the benefits I want to add in terms of the indoor air quality, the thermal comfort, and the energy consumption. Okay, so that was a quick run through of what if you fixed particular details. If you fixed the external noise level because you've already assessed the facade, what can you do in terms of varying the building form? Once you fix the building form, what can you do in terms of varying the ventilation type? And now I'm going to hand back over to Zay, who's going to look at what you can do in terms of shaping the facade for acoustic benefit.
Thank you, Owen. I just want to stress Owen's point. I think that the whole concept of this talk is to try and show that everything is interlinked. The greater the pressure that we have through an air vent, the greater the chance we have of attenuating the noise. If it isn't a particularly noisy site, the pressure becomes less important. But if it is a noisy site, designing and shaping a building, for example, the donut, is a very, very good way of reducing noise coming in through the building. What I want to talk about now is the benefits of shaping a vent, and can we maximize the acoustic performance of a vent mainly through its shape. If we start off by looking at how we specify the sound reduction of a facade stroke vent, we simply look at the external noise level, we subtract the internal noise level from that figure, and then there's a relatively simple correction factor that gets added to it. So those that want to do it as a rule of thumb, just subtract the internal figure from the external figure, and you'll more or less be there. For this particular example, I want to keep the internal noise level constant and show you this noise map that we've produced. What we see here is that as we travel away from the noise source, you can see that the sound level reduces. So if all of these require the same internal noise levels, they're all going to require different types of attenuation. And the different types of attenuation that we've got are taken from Jack's and Anthony's talk of a couple of weeks ago, where if we look at acoustic vents, balconies, attenuated windows, and then standard windows. At this point, we won't be talking about standard windows, but the work carried out by Napier University is very, very informative, and I would highly recommend a read. So if we start off with attenuated vents, attenuated vents are relatively simple, relatively crude device. Fundamentally, air flows over an acoustic the longer that absorption, the greater the level of attenuation. So in this particular instance, we've gone for a very cost-effective, standard openable window. These are on virtually every type of building. They're airtight, they're firm, they perform thermally very well. So the air travels in through the window, through the attenuator, and out into the space that we're attenuating. As I discussed, if it's particularly noisy, we simply make the attenuator longer, and that rubs out more sound as the air travels into the space. We then size the attenuator, the face area of the attenuator, along the requirements of the ventilation rate. It's important to note that there are different types of ventilators. What we saw earlier was one incorporating the window. Here we have a thermal damper with an attenuator placed behind it. In this case, we're hiding the attenuators underneath the seat, and here it's a very conventional design similar to this one, but in this case behind with a solar shading and rain protection. As Owen alluded to, I think it's important to recognize that the greater the pressure drop, the smaller the face area. Back to here, so this area becomes smaller. That means less sound is going to come through. The same amount of air is going to come through because you've got a greater force driving that air, and then that reduces the noise in turn. So cross ventilation is a highly effective form of noise control, and therefore I've included here a couple of details of some cross-socket attenuators into an atrium or into the center of the donut that Owen discussed earlier. In case of attenuated openings, I'll just provide a case study, which is Keynsham Town Hall. Keynsham Town Hall uses louvers on the facade. I particularly like this detail because it is a stunning building. Not necessarily reflected in this photograph here, but you can see the louvers on the outside, and then here you can see the final product, where the louvers are reasonably difficult to identify and forming part of the facade. On the inside, you can see the huge amounts of glass, and then the louvers on the elevation with a simple door opening them. The top doors here are controlled through a BMS system. So at night, there's thermal mass. So up here, there's acoustic absorption, and then this is a concrete plank providing the thermal mass for the daytime. Another illustration of the louvers. I mean, I think aesthetically, it's a CLT building. It is one of the most attractive buildings I think we've been involved in. So that's the attenuated openings. What I want to talk about now is balconies. Balconies was also alluded to in the previous talk. They are more difficult to incorporate into non-domestic buildings. They are becoming much more popular in domestic buildings, but BS 12354 provides guidance on how to select your balcony best. And I've provided a short video here to show you how the sound is controlled by balconies. So what we see here is the sound traveling out towards the building. The sound source is not located on the ground, so this second wave is a reflection. And you can see here how the sound is entering into the building, diffracting around the balustrading, reflecting off the top, diffracting through the space. So we can see the importance of treating these surfaces with acoustic absorption because it stops this reverberant effect. And this is also highlighted in BS 12354. As a case study, you can see here Winford Primary School. This is probably 2 miles away from the end of Bristol Airport. It is a fantastically noisy site. We have here the attenuators, simple windows. So the attenuators are placed outside in this case. The airflow is controlled by opening the windows. And then we're using these external play areas, which are covered, as a form of noise control. I'm not 100% convinced about the audio on this particular clip, but I hope it works for you. What we're going to listen to is the aircraft flying over the school, outside of the building, and then inside of the building, and then we're going to look at the noise inside the atrium as an aircraft flies over the top again. Okay, so that's an example of how you can use balconies and acoustic attenuators to prevent noise from getting into a building. If you go to that site, it is impressive. The undercarriages are down. It almost feels like it's shaking, and it's still a naturally ventilated building. And that is making the use of both attenuated openings and balconies. I want to talk about the final section, which is probably one of my pet subjects, which is how do we design air vents to reduce the amount of sound coming in through these elements. This is an image that used to be floated around CIBSE some years ago. It was a piece of work undertaken by a colleague of mine called Gavin Irvine in conjunction with Colt. And what he showed is that the sound reduction of an open window is between 10 and 15 dBs. However, if we created this baffle structure around the window, the sound reduction could be increased from 15 to 25 dBs, which is more or less in line with the research that we've been undertaking ourselves. So in terms of designing windows, it's important to understand that, unfortunately, I'm not 100% sure, but I'm pretty sure that the previous window wasn't sold on a single project. The reason for that is that architects like them to shape and to have an appearance on a facade that suits them, rather than to go and pick a product to whack into a building and make it look the same as some other building. So we've worked very hard to try and figure out what is the best way of designing a system that allows us to design unique elements for unique buildings, achieving the required acoustics and ventilation requirements. So the first thing that we need to do in designing a vent is to establish its sound reduction. The next process is to get an intuitive understanding of why and how that sound is passing in and through that vent. From there, we can then use 2D and 3D FEA modeling. We will only be presenting 2D, but we are using 3D modeling, and that gives us a reasonably good understanding of the actual physical sound reduction of the sound passing through the vent. And then the final part, of course, is that the best way of stopping sound coming through the vent is to close it. But of course, that's no good for airflow. So whatever we do to the air vent, we need to think very carefully about the airflow through it. And finally, we use the Hive, which is a facility that Bath University has developed to test facades, and we have our own acoustic facade testing rig at that location. So part of the inspiration for this came from my background, which was designing loudspeakers, and what we can see here is that the of loudspeakers has a significant impact upon their acoustic performance. Can we do the same for acoustic air vents? So the system that we've come up with is to use a piece of mathematics called finite time difference modeling. And what we do here is we create a grid. We stick a series of differential equations across that grid. And what that does is it allows us to model how sound will propagate through. We make that grid very small. We multiply that grid up, apply the structure that we are going to model, and here is the results. So what we see here is the sound traveling out, sound reflecting off the structure. We see diffraction down here, which is probably the most difficult element to model. And then we can see how the sound is propagating up. And out and into the room. I'm just going to rewind. The red element is absorption, so you can see that there's no reflection off of that. And it's these elements here that we were playing with to try and maximize the reduction of this particular window arrangement to try and maximize its acoustic performance. Finite element modeling is a very, very different type of modeling. Finite time different modeling provides you with a very intuitive understanding. It's reasonably accurate, but it's probably not as accurate as finite element modeling. Finite element modeling provides you with the final result of the sound passing through an object. Finite element modeling is a very similar element of code in that a mesh is used, as you can see here. But fundamentally, finite element modeling, you increase the mesh size around the key elements that you're looking to establish how the sound passes through. Finite time difference modeling is just a simple square mesh. And here are some results, and we saw some earlier. So this is the sound wave passing through a top-hung window, and now we're going to increase this baffle in here, and so forth. And now those of you that are into your ventilation, you will start to say, well, that's going to reduce the amount of airflow through your building. But if you're ventilating relatively low heat gain spaces, for instance, student accommodation. This might be more than enough air coming into the building, but you can see the significant benefit in the acoustics for very little additional cost. So the final section that I want to talk about is airflow. As I said earlier, there is no point in undertaking, in boosting the acoustic performance of the air vent if you don't get any airflow through it. So this is just a little bit of CFD that we've been looking at. And you can see here how the air passes through a window. These little balls are just representative. And as I was discussing with Owen this morning, this is relatively difficult. And those of you into CFD and those of you into extreme, or maybe not extreme, but technical airflow might criticize this. We have looked at extending the baffles down here and placing elements in front of the window. It is, in my opinion, a reasonably good indication of what is the air going to do. It is much better than just somebody sitting at a design table saying that isn't going to work. So that brings us back to the original page, which is how we design the acoustics of air vents to try and reduce the noise. And that's my final section. So I'll just hand you back to Owen to provide you with a conclusion of what we've spoken about.
Yeah, thanks. I think it is really interesting looking at those different tools that are available, the noise mapping, looking at the use of CFD, and it's quite easy sometimes for people to argue that there are deficiencies in the tools, which there always are, but it's about using them intelligently. Yeah, so the conclusions, coming back to actually the opening slide that we said we were going to address these three questions. Why are acoustics important to natural ventilation? Well, I think actually the fact that acoustics is one of the key drivers or the key tensions which pulls on natural ventilation design means that they are inherently linked, and they really can't be separated unless you are on a site which has no acoustic restrictions whatsoever. And then the second reason acoustics are really important is because of the health implications of creating an acoustically comfortable environment. You know, it is so beneficial to the people who live, work, study in that environment that they are given a comfortable place to do so. The different factors that pulled on ventilation we talked about, they were capex, they were energy cost, they were thermal comfort, they were air quality, and they were noise. And I hope we've demonstrated that they're all interlinked. And we've gone through a number of different tools that are available. We started off with the site mapping. We looked at different levels of quite simplistic site mapping, and we looked at the tools that ZE uses, which are much more involved, much more intelligent. We looked at 2D site mapping on a plane, but also turning that into a 3D model so that you can use it to infer the acoustics at roof level or higher up a building. And then we looked at how that leads into forming of the building and the building massing. And then we further went on to look at how that leads into the ventilation type you might select and how you can more intelligently design your ventilation openings, particularly windows, but also attenuated openings and other such, to balance those competing tensions. So I hope that's been an interesting and informative session. I would like to hand back over to Benjamin Jones and invite any questions.
Thank you very much, Zay and Owen. I've got a lot of questions here, so that's good. We've got plenty to talk about for the next 15 minutes or so. I just want to talk a bit, if I may, right now about some of the software that's used. A lot of great visual representations of sound and how your design can affect the quality of sound and the transmission of sound from the outside inside the building. Coralie Van Reenen asks, what software was used for the mapping? I would go on to ask for the finite time difference modeling. Is this your software? Is it proprietary, or is it somebody else's? And the same, I assume that the finite element analysis is probably something similar.
Yes, so the mapping is done using CADNA, which is fairly straightforward. The FEA modeling,
sorry, can you say that again?
CADNA, that's C-A-N-D-A.
Okay. Could you broadcast that by the text, please? That'd be helpful.
Absolutely. The finite element modeling was carried out using COMSOL, and the the FDDT was carried out using in-house software.
And that's something you've developed over the past few years?
Yeah, so what happened is we originally started looking at scale models of facades to try and predict their acoustic performance. The problem with that is it took too long. At stage 2, you only have a few weeks really to come up with a scheme that worked, and scale models was too cumbersome and too time consuming. And at the particular time, we had a French engineer who was looking at modeling the acoustics of wind instruments, and he was looking at finite time difference modeling. And then we've worked together with the Institute of Sound and Vibration through a couple of MSCs, developed that software in-house. We're not opposed to sharing it. It's not open source, but we wouldn't be 100% opposed to people using it.
Great. So let's go back to the sound maps, the noise maps. And here, Owen Clancy asks, how do you know that the noise maps are accurate? Do you somehow calibrate them with measured data? Do you go out into the field? Do you cross-check?
I think it's a good question. If you look at the first case study, the first case study just looks at 3 different layouts. It doesn't really matter whether it's accurate or it isn't accurate. You don't need to know how noisy the road is. You know that building next to the M32 is going to be a problem. And therefore, the layout of the buildings what it's showing you is the advantages of the layouts. You then might need to do much more detailed modeling to establish how noisy the levels are of the facade. The second case study very much shows you a calibrated noise level around a complex facade, because the existing school was made up of many buildings, and you can see that the calibration between the two is reasonably tight. There are a large number of complex assumptions that are made within the software that you need to be careful of. Our experience is that it's pretty accurate, and we've often gone back and calibrated the difference between what is on site, what we've modeled, and what we've measured on site. So there is a it's time consuming, it's expensive, but you can get very tight, accurate models. And we spend a lot of time doing that.
Okay, great. So often you don't have much say in the architectural form of the building. Given the choice, would you rather have holes in a vertical facade in a wall or in a horizontal facade in a roof? If you could influence the architecture yourself and persuade the architects to amend their geometry of their building, what would you go for?
I don't know if that's true that you don't have a lot of influence. I think there are plenty of examples where the natural ventilation design and the acoustic design have had very heavy influence on the facade of the building. I mean, Zay showed a number of examples where they do. I can think of a number of others which are, I mean, that building that I showed in one of my slides with the college in Dudley is very much being influenced by both the acoustics and the natural ventilation. So I think if you understand and make a compelling case, you actually can strongly influence it. In terms of would I rather have ventilation openings on the facade or the roof, you can probably predict that I'm going to say both, because that's the most efficient in my mind. What do you think, sir?
Well, I think Owen's making a bit of a joke there, but he's 100% right. I think that what we're trying to say is about it's about balancing the situation. If you have exceptionally noisy site, in my opinion, if you want to naturally ventilate it, you must do as much as you possibly can. The roof of the building, unless there's aircraft, is always quieter than the elevation, and therefore it makes perfect sense to put the ventilators on the roof or on the facade. I'm not sure if I fully understood your question. I thought some of your questions was whether it was a horizontal or a vertical vent. In my experience, if you're designing a school, vents are always horizontal. If you're designing an office, vents are on the vertical. I don't think it makes a great deal of difference between a horizontal vent and a vertical vent. It can make a difference to the airflow and the amount of pressure that you have, because the temperature difference between the inlet and the outlet can be different. That would then affect the opening area or the face area, and that would then have an effect on the acoustics.
I agree.
Okay, thank you. So So let's move on to the windows. Chris Ibn asks, so if you were to stand 1 meter away from a window, would you measure the same sound pressure level as you would measure, say, 10 meters away? And if they're different, then they're gone.
No, if they're different, what?
Well, if they're different, then surely you have a similar issue as you might with thermal comfort, in that people are more likely to be bothered by the.
I mean, I'm going to talk from my experience. My experience is that if you're a meter away from the window, you will get significantly louder noise sources than if you're at 2 meters away from the window. Once you're about 3 meters away, I would expect to see depending upon the size of the room, of course. Let's take a classroom or a 60 square meter office block. If it's a large office block of 100 square meters, the further away you move, it will get significantly quieter. We're actually undertaking a dissertation this summer looking at the use of ray tracing to predict the spread of sound into a building and to try and provide a correction for absorption. It's not necessarily absorption. If you put, if you have a reverb time, say 0.6, you won't have a diffuse field, and therefore you will have a bigger variation in sound pressure level as you move away from the window. My experience is that it's very rare that you sit within a meter of the window, and therefore there are at least 3 to 7 dBs of benefit that can be had by thinking about your window positions and where your seats are going to be. I think that is a definite bonus that can be used for to make natural ventilation a more successful design option.
Yeah, and if I can pick up on that same one as well, I think as someone who's not an acoustician, I'm a ventilation design engineer, but I have a basic understanding of the acoustics, and I do sit in meetings where people describe the work of acousticians as a bit of a dark art, and they don't fully understand it. And I think a better understanding of exactly that kind of question you ask, which is the difference between the sound power of a noise source and the sound pressure level experienced by a person in a particular location, is actually not widely understood, and we in the industry can do well to kind of publicize that knowledge a bit.
Okay. Now, I'm interested in the relationship between opening angle and the attenuation of windows. Another question posed by Chris Itten. So you, for example, you gave in your example the rule of thumb of 13 dB attenuation. But I know that when I open my window here in my office, just a centimetre or so, the ingress of noise is significant. Is there a linear relationship between the free area and noise from a constant source, or is it only non-linear?
I mean, let me give you a theoretical answer to that, if that's okay. If you have, let's say you take a sash window and you have a line source that's perpendicular to that sash window, what happens is that as you open that sash window, more and more power gets put into the room depending upon the opening size of the window. So there is a 10 to the log area relationship between the external level and the internal level. If you now take a top hung window and the sound source is opened directly in line with the opening, again, there is a direct relationship between the power going through that opening and the sound level in the room. So again, it will be relatively close to 10 log area. If you move round, so now there is no longer a direct line of sight between the between the sound source, apologies, and the opening, the sound enters the room as a process of diffraction around the edge of the window. And that is considerably more lossy than the power coming in through a window, and therefore you get an increase in performance. Now, the more you open it, the greater the chance of a power component coming back in. So there is a relatively complex relationship between the sound outside getting in and the sound inside, if that makes sense. It's quite difficult to explain without a drawing.
Okay, so you may not be able to answer this question if the relationships are noise complex, as you say. But Andrew Long says that you showed some FEA of noise ingress through different opening configurations.
That's correct.
Is there any conclusion for an opening type, i.e. an inward opening top hung high level, for example, that works best for typical low level ranges like traffic noise?
I mean, if you're opening inwards, you definitely get a beam of sound coming in through the window, so a bit of absorption. A while back, a reasonably large consultancy were drawing windows with acoustic absorption placed directly above them with them opening inwards. We've shown that through modelling to be reasonably effective. The use of the window sills can be quite effective. My advice would be to draw lines between the sound source and the opening, and you may require more than one line, and the more obscured those lines are, the better that window will perform. And you can get between 3 and 5 dBs of extra performance just by playing this game.
Yeah, it's something that Zay and I have actually been looking at together, is using the visualization tools that Mech Acoustics have developed to look at roof terminals, such as the mushroom cowl roof terminal that I showed on one of my images, and looking at how we could more intelligently place the acoustic attenuation that we use within those roof cowls. Yeah, I can show. I don't know if you want to quickly hand the screen back to me, Ben, but I could show a little video of that if you wanted.
Ben?
Yep. Okay. So this is a video, as I said, which shows a mushroom roof cowl, and as the video plays through, you'll see the noise impulse there.
Here's the reflections off the floor, the diffraction. You'll see here that there's a series of reflections, and here's even more sound coming through, and you can see the way it comes through at the top, gathering up here. So lining these surfaces down here isn't overly effective because the sound is already coming down. And you can see this sort of reverberant effect here, that if you manage to kill that off using the forms of absorption, it will become significantly more effective. Important is here at the entrance. That might restrict the airflow, but you could always offset this panel here slightly to allow for the absorption to go in.
Yeah.
Diffraction is difficult, and diffraction makes it unintuitive, but my experience is that what you would expect it to do usually does sometimes do what you expect it to do, if that makes any sense. Okay?
Okay. Yeah. So we've talked a bit about the you add insulation, or you add acoustic attenuation, but it has an effect on the pressure drop through an opening. So Lee Rong asks, in order to reduce the acoustic level with using an attenuated window, more layers may be needed. Then how do you coordinate pressure drop, which in turn affects the ventilation rate? How do you go about checking for that?
So we've used CFD. I mean, it's a very difficult question. What we found through research undertaken some time ago is that if you go for, say, a conventional attenuator with a 100mm splitter, the face of that is very disruptive to the airflow. If you then shrink it down to around the 50mm, even slightly smaller, the face area becomes significantly less disruptive, and the resistance of the attenuator is reduced. If you then make it even smaller, what then happens is you get the drag effect of the air traveling along the length of the attenuator, and that increases, and that causes you obviously an increase in pressure, which is negative. So there is actually a sweet spot in the splitter thickness, and the other game that we've played is to increase the surface area of the absorption using a honeycomb shape as opposed to a rectangular or a louver shape, and that is an effective way of increasing the acoustic performance of the attenuator, rather than with a smaller compromise on the pressure increase. There is obviously an increase on the pressure, but it is significantly smaller than if you start altering the thickness of the splitters and so on.
Great. Well, unfortunately, that's all we have time for today. I really want to thank our speakers, Zé Nunes and Owen Connick, for sharing their thoughts with us. If you want to listen again, a recording of this webinar can be found on the CIBSE's YouTube page in the very near future. Thank you for joining us, and until next time, goodbye.